Hi, I'm Diogo, the creator of Greenscale. Greenscale is a platform that provides a way to monitor sensors in greenhouses. It was designed with a scalable and modular architecture that optimizes computational resources. So this presentation will follow these points. It will start by talking a little bit about the overall platform architecture, followed by an overview of the different services, and the hardware, the future enhancements, and finally we'll look at the demo. The system needs to be designed in a way that provides an independently scalable architecture, almost like a modular approach. If you want to monitor more moisture sensors, you can orchestrate more containers to do so, without ever scaling the other service like a monolithic platform. The platform needs to follow the microservices architecture design. This allows the independent scalability that was required. This also provides a more efficient resource management and a lower running costs when compared to a monolithic approach. The platform also needs to be secure. Some shortcuts were taken in this department that will be discussed as the presentation goes. Each service was architectured in a way that allows each other to scale independently. To make this possible, some good practices rules were thought and applied. Services that need to retrieve information from other services can't send requests that take more than one hop. So a service can only send requests to services that doesn't have to request other service for information. This protects the platform from infinite loops when more services are added and the full architecture of the platform is not as easily perceived. Databases are only accessed through a service that provides a public API. This doesn't expose the ports to the internet. This allows logic to be added to protect the sensible data. Let's talk about the platform architecture. This image represents a simplified representation of the platform architecture. Every incoming HTTP request that hits the platform goes through the Nginx reverse proxy server on port 80, and then is routed to the respective service. The URI of the service follows the pattern API/API version/name of the service. This allows the maintenance of multiple APIs versions and better migration experience to new APIs. For example, if there's a bug on a new API that was catched in production, the team can push back the production build to an old API till the bug is fixed. All the MQTT traffic is handled by the broker that forwards the messages to the respective subscribed services and devices. The platform can either be orchestrated with Docker Container Orchestrator like Docker Compose and Kubernetes. Let's talk about the services. The platform implements multiple services, which are independent of each other. These services listed below are the ones currently implemented and which will be presented next. Future services can be implemented and added to the platform for additional service features. All backend API services are made in Python using CherryPy or Paho MQTT. Starting with the Nginx reverse proxy and load balancing server. Any REST request that hits one of the service need to pass through it. The server looks at the URL and redirects the request to the defined service. This hides the topology and characteristics of the backend servers by removing the need for direct internet access. The services on the platform are kept inside a non-public subnet and concentrated in the access control on that single point. The Nginx server always allows load balancing between the services, which is useful when there's a need to scale the platform. The cross-origin resource sharing, or CORS, is also controlled here. Now, the broker. The MQTT broker is handled by a Docker image of the Eclipse Mosquito broker. The configuration is the default one. The broker can be breached with others. For example, if there's a necessity to have a local broker in a Raspberry Pi, it can be done with minimal configuration on the local broker. There are plans to add WebSocket support for real-time data visualization in the future. User. The user service provides an API to the user's database through REST services. It handles the sign-in and the login of users. It also registers which greenhouse the user has access to. At this moment, there's no authentication in this service. I'm not very knowledgeable in authentication and web security, and the time to acquire that knowledge would overflow the time constraints to finish this project. So it's the biggest enhancement that needs to be done for the production build. The Greenhouse Services provides an API to the Greenhouse database through REST services. It handles all the information about greenhouses, their beds and sensors. Telemetry. The telemetry services provide an API to the telemetrics data. This service can be reused as a boilerplate for every type of sensor, so with telemetric I mean humidity, moisture, light for example. The service, when started, looks for an environment variable called telemetric that specifies the type of sensorial data that will be handling. Each telemetric services need to have its own database that follows the name convention db-telemetric, where telemetric is the one specified in the environmental variable. This provides independent scalability between telemetric services. If you want more moisture sensors than humidity sensors, you can scale the database and the service independently. Also, in case one of the telemetric server DB or DB goes down, the other telemetrics can still be able to post and get data. This service, the telemetric MQTT, provides an API to the telemetric database through the MQTT services. The client subscribes to sensor dash slash the type of telemetric slash hashtag. This will handle the public messages, verifying them and saving them to the database. Now, the web application. This service provides a web interface to interact with the platform. This allows the user to see the sensors, telemetry, and add greenhouses, beds, and sensors. This web application is fully built on React.js, a JavaScript library for building user interfaces. The UI components were all sourced from a library and UI framework called Semantic UI. The graphs were built using D3.js React wrapper called VX. On the production environment pipeline build, the web application is built in a Node.js Docker image and then it's copied to an image running Nginx, and the web application is served as static files on port 80. Search. This service provides a REST API to search for sensors, beds, and greenhouses. The service communicates with the greenhouse service to gather data, parses it, and returns the search data. At this point in time, the API only searches of sensors, providing an username and UUID. There is no access to the main database in this service. Depending on changes in the architecture, in the future it could have. Now the Discover service. The Discover service provides an API to the Discover database through REST services. The service handles discoverability of microcontrollers and their sensors. On power on, the microcontroller will send a GET request to the API, with the UUID and the username stored in the EEPROM. The API will send a request to the search service, questioning if the sensor belongs to the user. If it does, responds to 100 OK, and sends back the sensor data. If the response from the search service is 404 not found, the service will check if the sensor was already enrolled in a Discover database. If it is, responds to 100 OK and the sensor information with the username filled with the empty string. This lets the microcontroller know that wasn't assigned to a greenhouse. If the sensor is not in the Discover database, it is sent a 404 not found. This informs the microcontroller that it needs to enroll in the Discover service. To enroll in the Discover service, the microcontroller sends a POST request to the service containing the type of telemetric that will measure and the username. The service will respond back the sensor identification information. There's the discover enroll endpoint, where you can pass also a UUID. This allows the sensor to enroll in the platform with a UUID generated at compilation time when the programming of the microcontroller. The deletion of sensors enrolled in the service is taken care by the greenhouse service. When a service is added to a greenhouse, it will send a delete request to the discover service and it will remove it from the database. The hardware development was done through a NodeMCU development board that contains an ESP8266 microcontroller from Expressive with Wi-Fi capabilities. In the current state of the MCU, it connects to the Wi-Fi, enrolls in the Discover database, measures the data and sends the measurements to the server. The future full-fledged production-ready NodeMCU should be done in a different way, maybe using Platform.io Python pipeline build to enroll the sensors when the microcontroller is programmed. This makes possible to know which microcontrollers are legit. Due to time constraints, it was hard to properly develop an efficient code to support this. Now the enhancements. So future enhancements and problems that need to be taken care in future versions. The most important is security. Development of the platform, in some cases, security was put aside to make the prototyping faster. The low knowledge about web security would mean that learning it could delay the prototype for a few more months. So adding authentication is the most important thing to take care of. Make a better overall API for the services. This means improving the orchestration of the database schemas, smarter APIs and cleaner code, since the code is a little bit dirty from changes over time due to development requirement changes. Changing the programming language of services needing high performance and speed to more performant languages like Go and Rust. This will allow higher throughput with less hardware in services like telemetrics, where publishing data from millions of sensors needs to be efficient. Add support for WebSockets. This will allow the web application to update in real time the graphs and avoid useless requests. Study and choose a better database for the different services. Add support for warnings and actions on the system. This will allow the user to be informed in case of a failure or hazard events, and automatic actions will be taken. Make more than the monitoring platform. It is important to add support for user actions on the system, like automatic irrigation, management of airflow and light. Clean the code of the web application. There are some component re-renderings that can be improved for better performance. Add support and boilerplate for custom services, and make a PCB with ESP8266 to make the system more user-friendly and make the plug-and-play experience better. Now with the demo, it will be done in two parts. The first will show the hardware working with the platform, and the second will spawn a lot of users and traffic to simulate a real case scenario where sensors are publishing regularly. Okay, so now let's start the hardware demo. We'll open the terminal, we'll go to the project folder, then go to the services folder and start the platform. I've already created a user so we can speed up the testing. If you go to localhost, you can see the web application, and if we go to the database, the main database, we can see we already have one user with one greenhouse. Let's go to that user. Okay, so this user has a greenhouse, a bunch of beds with a bunch of sensors. So let's turn on some of the Node MCU microcontrollers. I have two here. This one has two sensors, one of humidity, one of moisture, This one has one of moisture. I will turn just the one of this one only, then the other. And this will activate the Discover service, and then we will enroll this sensor in the Discover service. If we try to add now a sensor, we see that we don't have any sensors enrolled in the discovery, so we have to enroll this one. So I will turn this one on. Okay, we can check the command, the output in here. If we go to here, you can check this measuring. Let me restart this one. Okay, it's connecting to the internet. It enrolled, and now it's publishing data. Okay, so if we now go to, we can see that we received some requests on the services. If we now try to add we can see that Beans doesn't have that sensor. If we try to add the sensor, we can choose the Beans bed, and now there's the sensor. We add the sensor. If we now go to here, we can check the sensor data that is publishing. Okay, now let's turn the other one on. Okay, we will receive here some requests. The discovery service. Try to enroll. I think we can add those two cabbages. Okay, sensors. Cabbages. Okay, we have the new two sensors that we added. Okay, let's add the moisture one, and let's add the humidity one. Okay, can check both of them. They are publishing. Can wait to refresh they are publishing. And this is the hardware this is the hardware, and it's functioning. We are seeing requests coming. Yeah. So now let's do the real test. Let's generate a bunch of users and let's see if it can handle. Let's go to the test folder. I've done some scripts. I'll run the REST bot1. So we can check the help. Okay, not this one. PY. Can run this. So let's just verify that's nothing on the database. Okay. So let's run 10 bots because it's on my computer and it's transcoding the video. Okay. Generating the greenhouses, the sensors, the beds. Generating between 10, I think, for each user, between 10 greenhouses, for each greenhouse between 10 beds, sensors. Okay, it's posting the data. So let's just check the database, and we can see that we have now users. We have 7 documents. Okay, we have 10 documents, 10. Okay, so let's check one of these users, maybe this one, Ariana 693. If we go to the platform, we can check that he has a bunch of greenhouses. So let's go to Rome, strawberries. So let's check this moisture, and maybe the oranges. We can check the humidity. If we go to Torino, we can check the cucumbers and the moisture. Okay, the sensor is publishing between, I think, 5 to 10 seconds here for each sensor. It's running a thread for each one. Okay, we can see that some data is coming. Can wait a little more. Okay, my computer is getting hot. Okay, and we can check that data is coming. We can trail some of the sensors. Okay, we can see the moisture. Let's just set a little bit more to... The dates are kinda not wrong, but it's the best I could do with D3. Okay, it's enough. You can see the data coming. For more information, so you can go to github.com/dvclaire-greenscale. Here you can find everything, documentation, everything. So thank you for watching and bye.